So if you've ever had to build a system that handles thousands of connections at once, like a modern web server,
Yeah.
a database layer, really anything that spends most of its time just waiting for the network or a disk, that bottleneck.
Oh, yeah.
You have all this processing power, but your application is just stalled, doing nothing.
Yeah.
And the question is, how do you manage all those tiny waiting periods efficiently without the whole thing just collapsing?
That waiting time, that I/O gap, is really the biggest challenge in high concurrency architecture. And the answer, the solution we're diving into today, is the coroutine.
Right.
And forget the simple definition. The real power of a coroutine is its ability to voluntarily suspend its own execution, usually when it hits that I/O wait. But the key part is it preserves its entire internal state, all its variables, completely intact until it's ready to resume.
So it's not just pausing. It's like taking a perfect snapshot of its progress in memory. It's cooperative multitasking, but purely at the software level.
Precisely. That voluntary suspension, that ability to yield control back to a scheduler when you're not doing anything useful, that's what unlocks just massive scalability.
Okay, so let's unpack this. Our mission today is a deep dive into how coroutines are implemented in three major languages: Python, Rust, and modern C++ Carry.
Three very different philosophies.
Exactly. From the high-level simplicity of Python to the extreme low-level control you get with C++ Car. We want you to walk away from this knowing which tool really fits your job best.
Whether that's speed, safety, or just getting something built fast.
So let's start with the essential why. We mentioned threads are heavy. Can you break down why coroutines are so much more efficient for these I/O-bound tasks?
Yeah, it really just boils down to two things: context switching cost and memory footprint. Think about traditional threads.
Okay.
They're managed preemptively by the operating system kernel. So when one thread has to wait, the kernel itself has to step in, save the entire state of that thread, and then load the state of the next one.
And it sounds like a lot of heavy lifting for the OS.
It is. It's a very costly system call. And on top of that, each thread needs a big, dedicated stack. We're talking megabytes of memory per thread. So if you try to spin up, say, 10,000 threads,
You're in trouble.
you've just eaten up dozens of gigabytes of RAM before you've even done any work, and your CPU is just spending all its time managing these context switches.
That just seems completely unsustainable for the kinds of systems we need to build today.
It is. And this is where coroutines just shine. They run on a single OS thread or maybe a small tool of them. The context switching is cooperative, and it happens entirely in what we call user space.
So the OS isn't even involved.
Right. The software framework, not the OS, saves only the bare minimum state it needs. The difference in memory is staggering. A coroutine might take a few kilobytes, maybe even less, compared to megabytes for a thread.
Orders of magnitude.
Absolutely.
Yeah.
This is what lets you handle hundreds of thousands, even millions, of concurrent connections with way fewer resources.
The performance gain is obvious, but there's another side to it, right? The readability. Anyone who's had to debug code with layers and layers of callbacks knows what callback hell feels like.
Oh, it's a nightmare. Coroutines completely fix that. They let you write asynchronous logic that looks sequential. Instead of a messy callback, you just put an await or a yield keyword right there in your code.
And it just reads top to bottom, the way you'd naturally think about a process.
Exactly. It makes maintaining and debugging so much easier. So we're talking about everything from network requests, file operations, database queries. Coroutines are really the backbone of modern non-blocking I/O.
Okay, let's shift focus to our first language, Python. Its whole philosophy is about developer experience, getting things done quickly. How does it handle something as complex as coroutines?
Well, Python's modern async model is actually built on something much older and simpler: generators.
Right, using the yield keyword.
Exactly. Yield was first used to create iterators, functions that produce a series of values over time, pausing after each one.
That idea of pausing and resuming sounds very familiar.
It's the absolute foundation. Yield is the mechanism that pauses the function, and this is the critical part, preserves its entire local state. All the variables, loop counters, everything. Python's creators realized this state-preserving pause was powerful enough to be extended.
So yield gives us the pause, but today we all use async await. How are those connected?
Async await is basically a much cleaner, more focused syntax that's layered right on top of that generator model. When you write an async det function, Python kind of turns it into a special generator that works with an event loop, like the one in Asyncio.
And the event loop is the scheduler, deciding who runs next.
Yep. It's what wakes up the right coroutine when its I/O operation is finally done.
You brought up a really great example to show how elegant that state preservation is. The Steinhaus-Johnson-Trotter permutation generator. It's a mouthful, but why is it such a perfect illustration?
It's perfect because the algorithm itself is so stateful. It generates all possible permutations of a set of numbers. But to get the next permutation, you need to know the current arrangement of the numbers, the direction each one is moving, and other indices.
So if you were writing that with normal functions, you'd have to manually pass all that state back and forth on every single call.
Exactly. It would be a mess. You'd return a permutation, then have to pass it right back into the function along with all the direction flags just to calculate the next step. But with a Python generator using yield, the function just calculates and yields the next permutation, and then it goes to sleep.
Mm.
All those internal variables, the array, the directions, are just kept alive inside the coroutine state automatically.
It just works.
It makes a really complex stateful iteration look trivial. It's all about developer velocity and making complex state management feel simple.
Okay, so if Python is all about simplicity, let's pivot to Rust. Rust's goals are completely different.
Performance and what it calls fearless concurrency. What's its architectural approach? Rust takes a much more explicit and structural approach to guarantee safety. The key building block isn't a simple generator, it's the future trait.
A future, so it represents a value that isn't ready yet.
Exactly. Any function you write with async evn in Rust literally compiles into a structure that implements this future trait. It's basically a dormant state machine.
And async await is just how you interact with that state machine.
Correct. It's what we call zero-cost syntax for working with futures. But here's the crucial difference from Python. Rust makes you explicitly separate the coroutine's definition, the future, from the component that actually runs it.
The executor.
The executor, yeah, which is provided by a separate runtime like Tokio or async signer. The executor is what actively pulls the futures over and over, driving them towards completion.
The collaboration feels important, and it must be connected to Rust's big advantage, those compile time guarantees.
This is where Rust is just exceptional. It gives you true zero-cost abstractions. The compiler takes your high-level async code and flattens it into an incredibly efficient state machine. No runtime overhead. But the real game changer is the borrow checker.
Okay, tell us how the borrow checker works with async code specifically.
So every single time a coroutine suspends in Rust, at every await point, the borrow checker scrutinizes your code. It makes sure that any data you're referencing across that suspension point is managed safely.
What does that mean in practice?
It means it stops you from, say, holding a mutable reference to some data that another concurrent task might change while your coroutine is paused.
Wait, so you're saying the compiler is actively preventing data races before the code even runs?
Precisely. If you try to write async code that could be unsafe, the compiler will just refuse to compile it. This is what fearless concurrency is all about. You get this mission-critical safety and reliability without sacrificing a single bit of runtime performance.
That's a huge philosophical shift. It's not, let's hope we catch the bug at runtime. It's, let's make it impossible to write the bug in the first place.
You got it. All the hard safety work is done up front by the compiler.
All right, from the safety of Rust, let's cross over to modern C++, specifically C++20. If Python is ease and Rust is safety, C++ is all about unparalleled control and flexibility.
The lowest level of abstraction, for sure.
What does a developer get by taking on all that extra complexity?
C++20 coroutines are different because they're not a full runtime environment. They're more like a low-level language framework that lets you build your own async systems. You get the keywords cowait, coiled, coreturn, and then you, the developer, have to build all the machinery around them.
It sounds like the language gives you the engine parts, and you have to assemble the car.
That's a great way to put it. And the central component you have to build is something called the promise type.
The promise type.
Yeah. You have to define one for every kind of coroutine you create. And this promise type controls everything. How memory is allocated for the coroutine, whether it starts right away or suspends, what happens when it's done, how the return value is handled, everything.
That is a massive amount of responsibility. But I imagine it unlocks some serious optimizations.
It really does. Things that languages with fixed runtimes just can't do. For example, C++ allows for something called symmetric transfer. This is a super low-level trick where one coroutine can suspend itself and transfer control directly to another waiting coroutine.
Without even going back to the main scheduler.
Exactly. You bypass even the user space scheduler we talked about. When every microsecond counts, that ability to hand off execution directly can give you peak efficiency. You're basically handcrafting a perfect state machine.
And C++ Also lets you use template metaprogramming with coroutines. What does that do?
Template metaprogramming lets the compiler do a ton of work during compilation, not at runtime. So you can write a generic coroutine, and the compiler will generate code that's hyper optimized for the exact data types you're using.
So the final binary is as fast as if you'd written it by hand in assembly.
That's the goal. C++ is for when you're willing to trade developer time and complexity for absolute granular control over every clock cycle.
Okay, that brings us to the comparison. We have simplicity, safety, and control. When we put these three side by side, what's the decision framework here?
The sources really show a clear trade-off triangle. Python gives you the highest ease of use and developer velocity. It's fantastic for prototyping. The trade-off is, higher memory usage, and it's generally slower.
Right. Then there's Rust.
Rust wins on safety, hands down, because of those compile time checks. And its speed is right up there with C++A, but with very low memory usage. The downside is that it has the steepest learning curve.
And finally, C++I.
C++ is the ultimate performance champion. Fastest speed, maximum control. But that power comes at a cost. It's the least safe because you're managing so much yourself, and it is by far the hardest to use correctly.
And it's important to note all three have really mature ecosystems now. Python has Asensio and Fast API, Rust has Tokyo and Axiom, C++ has libraries like CPP Coro. So the choice is really about your project's needs.
Absolutely. The decision framework is pretty clear. Choose Python if your priority is rapid development and you need a huge ecosystem of libraries.
Okay.
Choose Rust if your project is mission critical, where you need that killer combination of performance and compile time safety.
And finally, choose C++ if you're doing low-level system integration, building embedded runtimes, or you just need that absolute max zone control over every little detail.
3 excellent tools for the same problem, but with totally different philosophies.
So to wrap this up, coroutines are clearly the answer for efficient concurrent code. But how do you actually apply this in a large, real-world system? What's a common pattern?
The classic one is the producer-consumer pattern. It's an architecture that uses coroutines to decouple tasks from each other using a central queue or a channel.
So one coroutine, the producer, creates work, and another, the consumer, does the work.
Exactly. And the queue sits in the middle, handling the synchronization. Maybe a producer is scraping a website, it gets some data and puts it on the queue. The consumer is the part that writes that data to a database.
And if the database gets slow, the consumer slows down.
The queue starts to fill up, it handles that back pressure. It can even tell the producer to pause for a bit so they cooperatively balance the workload. It keeps the whole system stable.
We see this pattern everywhere. And each language has its own tools for it.
Yep. Python has asensio.q. In Rust, you'd use a channel from Tokyo. The coroutine is what makes that elegant balancing act possible.
Looking forward, this whole landscape isn't standing still. We're seeing some really interesting trends emerging.
Yeah, there's a big push toward what's called structured concurrency.
Mhm.
The idea is to make error handling and cancellation much simpler and more reliable.
So no more fire and forget tasks that get lost.
Right. If you start a group of related tasks, you can reliably wait for all of them to finish. Or if one fails, you can safely cancel all of them together. It makes error propagation predictable. Python's task groups are a move in this direction.
And there's an even more radical idea on the horizon, effect systems.
This is like the next evolution of what Rust is doing. It's about baking asynchronous behavior directly into the type system itself. So if a function performs I/O or can pause, the compiler knows this as part of the function's type, its effect, and it forces you to handle that possibility.
That's a massive step toward making these incredibly complex systems both fast and provably safe. So we'll leave you with this question. As you think about your next project, which of these innovations, the guaranteed robustness of structured concurrency or the enhanced safety of effect systems, will fundamentally change how you write concurrent code next year?
A fantastic deep dive. It really shows the engineering trade-offs at play in modern software.
When that wraps up this deep dive,